All right, we're going to go through the study guide for exam 2. But before we do that, I want to have the another thing that you need to know, and that is activity series. All right, so your activity series, you're going to have metals, and then you're going to have halogens. All right, and you just have to know the top 4 metals. The most reactive metal is potassium, followed by calcium, followed by sodium, and followed by magnesium. So these are the top 4. So you have to know the top 4 metals in the activity series. And then your halogens are just the order of the periodic table: fluorine, chlorine, bromine, iodine. All right, now the metals, so this is what you have to know. So memorize these. So this is the most reactive, most active, most reactive. All right, and so these are to be memorized. You do not memorize the rest of the list. The rest of the list, if you need it, it will be given. But in the problem, you're going to have one of these 4. All right, so if you want the rest of the list, it is then aluminum metal, zinc metal, iron, nickel, tin, lead, hydrogen gas. That is a not metal, but again, hydrogen sometimes pretends it is a metal. All right, then copper, then silver, mercury, and gold. All right, so this order doesn't really matter unless you're working a problem that uses these metals to see if a reaction occurs or not. All right, on the test, all you have to worry about are the top 4. So the question on the test, which is the question on the study guide, is your magnesium reacting with your HCl. So the question is magnesium plus HCl. All right, so this is for a single replacement reaction. All right, and so magnesium is the top 4. It's in the top 4. It's one of the most reactive metals. And so this one will react. All right, and so what happens is the metal replaces the positive ion. All right, and so that is hydrogen, which is down here, less reactive. And so you end up with MgCl2 and hydrogen gas. All right, if you do to balance it, you put a 2 in front of your HCl. And so this is oxidation reduction. So all of your single replacement reactions are also oxidation reduction. All right, and you know that by doing the oxidation number. So magnesium solid metal off the periodic table, that has an oxidation number of 0. Hydrogen in compounds is going to be +1 unless it's with a metal. The chlorine in binary compounds, -1. Magnesium on the right is magnesium +2. Chlorine is -1. Hydrogen gas, hydrogen, elemental form, 0. Any element in its natural state has an oxidation number of 0. All right, so you can see by doing the oxidation numbers that the Mg is going from a 0 to a +2. So that is your oxidation. Your hydrogen is going from a +1 to a 0. So that is your reduction. All right, so for all of your single replacement reactions, it is oxidation reduction. And so you can list your reducing agent. So your reducing agent is your magnesium. Your oxidizing agent is your HCl. Remember, your agents are reactants. So you can't just say hydrogen because hydrogen is not the oxidizing agent. Hydrogen is a product the oxidizing agent is the HCl. All right, it has to be a reactant. The reducing agent is a reactant. The oxidizing agent is a reactant. All right, so don't label the atom that's changing oxidation state. Label the reactant that is changing the oxidation state to get the reducing agent, oxidizing agent. So this reaction occurs because the magnesium is more reactive, so it will kick out the hydrogen. If you did the reverse reaction and I had hydrogen gas plus MgCl2, all right, so here the hydrogen gas is less reactive than the magnesium, and so this would be no reaction. So you would simply write NR or an Lb2, leave everything blank and push enter because nothing, you get no reaction, nothing is formed. If we did iron, well, that'd be the same thing. So instead of picking the hydrogen gas, I could pick iron solid metal plus MgCl2. Same thing. This is one of your top four. This is not one of your top four. This is no reaction. If I picked potassium metal with lead nitrate, lead 2 nitrate. All right, so this is one of your top four. Potassium is number one. So this is the most reactive metal. And so it is going to kick out the lead. And so you're going to end up with KNO3 and lead solid metal. Well, lead is, lead solid metal. So we have, to balance it, we need 2 of those and 2 of these. So again, it is oxidation reduction. Potassium is going from 0 elemental form to always in compound plus 1. The lead here is a plus 2 lead, and it's going to the elemental lead of 0. So we are oxidizing the potassium, and we are reducing the lead nitrate into lead. This is the reduction. All right, so this is your oxidizing agent, the whole thing here, not just lead. It is the lead nitrate that is your oxidizing agent. So if we wanted to take potassium and oxidize it, we go to the stockroom and we have to pick something that will oxidize it. So that's why it's called an oxidizing agent. So the lead nitrate will oxidize the potassium. All right, and so this is your reducing agent. If we wanted to reduce lead nitrate, we add potassium, it will do the reduction. All right, if we tried, let's see, let's try another reaction. Let's do F2 plus NaBr. All right, and so the question is this reaction going to occur? Again, you go to your activity series and it's the periodic table. F2, Cl2, Br2, and I2. All right, and so the most reactive is fluorine. So yes, anytime you have fluorine, it is going to kick out a halogen. So when you're doing the halogens, one halogen is replacing another halogen. When you're doing the metals, one metal replaces the other metal. Again, hydrogen sometimes thinks it's a metal. So hydrogen is a gas, but it reacts like a metal. All right, so this will kick out the bromine. And so you're going to end up with NaF, and then you're going to end up with Br2. All right, so to balance it, you need 2 of those, you need 2 of those. Now, fluorine is a gas, and bromine is a liquid. All right, and so I'm not really concerned with labels, solids and liquids and gases on the single replacement. All right, but we can also do the oxidation reduction. So fluorine here is in its elemental state, so it is 0 oxidation. Fluorine in binary compounds is -1. Bromine in binary compounds is -1. Bromine, elemental, bromine, 0. All right, and so when you're going from a 0 to a -1, that is your reduction. And when you're going from a -1 up to 0, that is your oxidation. All right, and so your fluorine is the oxidizing agent, and your NABR is your reducing agent. So whenever we're doing oxidation reduction, you're going to have to label the oxidation numbers and tell me the oxidation half reaction, the reduction half reaction, the oxidizing agent, and the reducing agent. All right, so let's continue with the study guide for exam 2, which is on Moodle. And so the first question was Mg solid plus HCl. All right, and so since magnesium is in our top 4, it is going to replace this metal, but this is not a metal, this is hydrogen. It will replace hydrogen acting like a metal. And we're going to get MgCl2 and H2 gas. All right, and so to balance it, we just put a 2 out in front of the HCl. All right, so this is your molecular. Now to get ionic, any solids, liquids, and gases stay together. Magnesium solid stays together. All right, now your acid, all acids are aqueous. You only break up the strong acids. Remember the 6 strong acids. You must know the 6 strong acids: HCl, HBr, HI, HNO3, HClO4, and H2SO4. All right, so you have to know those 4. You have to recognize, yes, HCl is one of the 6 strong acids. And so it breaks up into 2 H plus and 2 Cl minus. MgCl2, you have to know your rule. And the rule says for halogens, all halogens are soluble except for silver, mercury, and lead. This is magnesium. It is soluble. And so it's Mg plus 2 and 2 Cl minus. Anytime you have a solid, liquid, or gas, you leave it as written, H2 gas. All right, and so when you ionize completely, that means you are a strong electrolyte. Every strong acid is a strong electrolyte. Every soluble compound that is ionic is a strong electrolyte, which means it goes completely into ions. All right, and so to get to the net ionic, you see that 2 Cl minuses will subtract 2 Cl minuses, and you have Mg solid plus 2H plus yields Mg plus 2 and H2 gas. So that is your net ionic, and the spectator is what canceled out. That's the Cl minus. So your spectator is Cl minus. All right, so the second part of that is going to be, we got 20 grams of magnesium. All right, and it says it's going to react with 50 mils of 6 molar HCl. All right, and then we're going to produce MgCl2, and it produces 10.8 grams of MgCl2. All right, so then the question is to calculate the limiting reagent, theoretical yield, and the percent yield. So limiting reagent, theoretical yield, percent yield. There is a 100% chance that a question just like this will be on the test. All right, anytime you have limiting reagent, theoretical yield, percent yield, you always have to work in moles. Then you use the balanced chemical reaction, use that mole ratio. 1 mole of magnesium reacts with 2 moles of HCl to produce 1 mole of magnesium chloride and 1 mole of hydrogen gas. All right, so we have to go from 20 grams of magnesium to moles. All right, and so you go to the periodic table and you see the molar mass of magnesium is 24.31 grams per mole, Mg, right off the periodic table to 2 decimal places. All right, Now they give us information on MgCl2, so we then use the mole ratio to go to moles MgCl2. We see that 1 mole of Mg will produce 1 mole of MgCl2. So 1 mole Mg will produce 1 mole of MgCl2. So moles of Mg cancel moles of Mg. Grams of magnesium cancel grams of magnesium. All right, and so since the answer that they gave was in grams, 10.8 grams, then we will go to grams. So the molar mass of MgCl2, 24.31 plus 35.45 times 2. So this is your magnesium, this is your chlorine, this is off the periodic table. Push the buttons on your calculator and you get 95.21. So you get 95.21 grams MgCl2 per mole of MgCl2. All right, so then you push the buttons on your calculator to get that mass. So you take your 20.0 divided by 24.31 times 1 divided by 1 times 95.21. And that gives you 78.3 grams. That is a 78.3 grams of MgCl2. All right, so now we got to do the same thing for the HCl. Note that the mole ratio is 2 moles of HCl to 1 mole of MgCl2. All right, so for this one, we have 50 mils of 6 molar. So when you have 6 molar, molar does not help. You have to know that that is moles of HCl per liter of solution. And they tell us that we have 50 mils of this solution. So you have to convert that to liters to cancel liters. So 50.0 M is times 10 to the minus 3 liters. All right, so this is then moles of HCl. All right, when you're given a mass, you got to divide by the molar mass to get moles. When you're given a molarity, you multiply it by its volume to get moles of that reactant. And so from our balanced chemical reaction, we saw that 2 moles of HCl produced 1 mole of MgCl2. And then we want that in mass, in grams. And so we have to again take the 95.21 grams per mole for your MgCl2. So now we take our 6.00 times 50 times 10 to the minus 3 times 1 divided by 2 times 95.21. And we get 14.3 grams. All right, so this is the lower of the two values. So the lower of the two values, that is the theoretical yield. Which comes from the limiting reagent. All right, so once you have calculated your two numbers, you got your 78.3, you got your 14.3. The lower of the two, that's your theoretical yield. That comes from the limiting reagent, which is a reactant. And this one, your choice is between magnesium or HCl. HCl is your limiting reagent because it produces the least amount of product. And that least amount of product is your theoretical yield. Now to get the percent yield, you have to take your actual divided by theoretical times 100. Actual has to be given. It says 10.8 grams was produced. So you take your 10.8 grams that was produced over the 14.3 grams that was the theoretical yield, which means that's the most you could possibly get. All right, so times 100. So then you take your 10.8 divided by your 14.3 times 100, 75.5. So you get a 75.5% yield. And that's as hard as the problem can get. It is hard because you were given a molarity and a volume. And so most people can go to moles from grams and just use the molar mass. But molarity and volume, if you don't know what capital M is, it's impossible to get to moles. Capital M is not moles. Capital M is moles of your solute, in this case HCl, per liter of solution. So there's guaranteed to be one of those on the test. Make sure you can do a limiting reagent and theoretical yield and percent yield problem. Percent yield is pretty simple. You stick your actual over theoretical. All right, so the next question is, how should you prepare, all right, 50 mils of 6 molar HCl? From 12 molar HCl. All right, so when you buy HCl, it comes 12 molar, very concentrated, and so you have to then dilute it to whatever concentration you need for your lab. In this lab, it requires 50 mils of 6 molar HCl. So you get your bottle that you buy, and it's 12 molar HCl. So we have to dilute it. So the equation for dilution is M1V1 is equal to M2V2. All right, so M1V1 is equal to M2V2. All right, so we have 6 molar HCl, and we have 50 mils of that. We are going to use 12 molar HCl, and we need to know what volume of that we need. All right, so you simply divide both sides by 12.0. And your volume is 25. All right, so that is not the answer to the question. If you say, how should you prepare 50 mils of 6 molar HCl from 12 molar HCl, and your answer is 25 mils, that is not preparing anything. That is saying 25 mils. All right, so you have to explain what you're going to do with the 25 mils. All right, so you're going to take, this is an acid, very concentrated. Remember, you have to add acid to water. All right, so we're going to take a 50 mil volumetric flask. All right, so here's a volumetric flask. So we're going to use a 50 mil volumetric flask. And all right, so we're going to add, I'm going to go with 24 mils of water. All right, and so then I'm going to add 25.0 mils of 12 molar HCl. All right, so again, you have to have water in there. Then you add the acid to the water. Always add acid to the water. And then the final step, anytime you're making a molar solution, is dilute to the mark. So you're going to add 25 mils of your 12 molar HCl. And then dilute to the 50 mil mark with water. All right, so it's always dilute to the final volume whenever you're doing a molar concentration. All right, so always you add acid to water to disperse the heat. Do not add the water to the acid. All right, so you put in some amount of water. What you have to make sure is that the amount of water plus the amount of acid has to be slightly less than the total volume that you need. So when you're adding 24 mils of water, then your 25 mils of 12 molar HCl, you have to make sure that that does not go above your 50 mil mark, because then you can't dilute to that mark. You're already above it. All right, so you have to make sure that that is less. All right, so the additive volumes have to be lower than the total volume so that you can dilute to the mark. But you want as much water as you can get to disperse that heat. Right? So for that lab, we also need 50 mils of 6 molar NaOH. So we need to prepare 50 mils of 6 molar NaOH from solid NaOH. All right, so when you buy your HCl, it's a liquid, it's 12 molar. When you buy your NaOH, it's a solid. All right, and so this one, we have to weigh out some solid, dissolve it in water, and then again, when you're making this, you always have to say dilute to the 50 mil mark. All right, so first we have to figure out how much NaOH we need. Well, if you know what capital M is, that is moles NaOH per liter. And this is our volume in milliliters, so we have to convert that to liters. All right, so we have 6 moles of NaOH per liter of solution, and we have 50.0 times 10 to the minus 3 liters. All right, so I just get rid of the M, and I know that's 10 to the minus 3, and now I have the correct unit, liter and liter. That will cancel. All right, so moles of NaOH, I don't have any way to measure moles in the lab. I have a balance, I can do grams, and so I go to the periodic table and find Na, which is 22.99 grams per mole, and I find O, which is 16.00 grams per mole, and I find H, which is 1.01 gram per mole, and I add those up, and it's a perfect 40.00. And so now it is 40.00 grams per mole. And when I push the buttons, I have 6.00 times 50 times 10 to the minus 3 times 40. I get 12. All right, so I have 12.0 grams NaOH. All right, so if I say, how do you make that solution? And you say 12 grams of NaOH, I'm standing here with 12 grams of NaOH. That is not a solution. All right, so you have to then say what you're going to do with this 12 grams of NaOH. All right, and so here is what you should do. So you're going to take, again, your volumetric flask. So you got your 50 mils volumetric flask. And I'm going to add, I don't know, let's say 30 mils of water. Then I'm going to dissolve 12.0 grams of NaOH. All right, so I put in my water, goes to about there. All right, then I'm putting in my solid, my 12 grams of NaOH, and then I'm going to swirl it until it dissolves. All right, once it has dissolved, then I dilute to the mark. All right, so you add water until you get right to that mark. Remember, a volumetric flask has a long neck. All right, and on a volumetric flask, there's only one mark. And so if you have a 50 mil volumetric flask, that mark is for 50 milliliters. All right, so anytime you're making a molar solution, it always has to be then finally dilute to the mark, dilute to the final volume, whatever the final volume is. In this case, it asks for 50 mils. So you would then dilute to the 50 mil mark. All right, so number 4 on your study guide says calculate percent magnesium in magnesium chloride. So calculate percent magnesium in MgCl2. So this is a very simple question. If you know how to do it, it is very simple. All you have to do is go find the molar mass that we already did. So magnesium's molar mass, 24.31 grams per mole. Chlorine molar mass, 35.45 grams per mole. But we have 2 of them in MgCl2. And when you added that up, you got 95.21 grams per mole. And so you just take the mass of magnesium divided by the mass of the magnesium chloride times 100. So you take your 24.31 grams per mole and divide by the total, which is 95.21 grams per mole. To get a percent, multiply by 100. When you take your 24.31 and divide by 95.21 times 100, you get 25.53. All right, now note that you have 4 sig figs divided by 4 sig figs, and this multiplying by 100 to get percent, that is a perfect 100. All right, so 4 sig figs, infinite sig figs, 4 sig figs in your answer. If you wanted the percent chlorine, they have to add up to 100%. So that would be 74.47% chlorine. You could also get that same answer by taking your 70.90 grams per mole, dividing by the 95.21, and multiplying by 100. That would also give you 74.47% chlorine, because the magnesium percent plus the chlorine percent must equal 100%, because magnesium chloride only has magnesium and chlorine. All right. Calculate, so number 5, calculate the molecules of MgCl and 20 grams of MgCl2. So calculate molecules of MgCl2 in 20 grams of MgCl2. All right, so when you see the word molecule, all right, so that should remind you to use Avogadro's numbers, 6.022 times 10 to the 23rd. This is molecules or atoms in this chapter, but this is molecules because that's what we're doing in this problem per mole. All right, so when you have 20 grams of MgCl2, and we just did the molar mass, which is 95.21 grams per mole, you can convert grams into moles, and then you can convert moles into molecules. All right, so your 20 grams MgCl2 divided by the molar mass, which is 95.21 grams per mole. And then Avogadro's number, which is 6.022 times 10 to the 23rd molecules, MgCl2, per mole MgCl2. So the moles of MgCl2 cancel the moles of MgCl2. The mass of MgCl2 cancels the mass in grams of MgCl2. And when you push the buttons on your calculator, 20.0 divided by 95.21 times 6.022 times 10 to the 23rd gives you 1.26 times 10 to the 23rd. All right. So whenever you're talking about molecules, you're going to have a giant number of molecules. Molecules are very tiny. All right, so in part B, it asks for how many atoms. Calculate atoms. Of chlorine in 20 grams of MgCl2. All right, so once you have your molecules, or you can go through all the steps again, it will be the same steps. You go from grams to moles, moles to molecules, because MgCl2 is a molecule. And if you see that you can keep going here, now you can have 2 atoms of Cl in 1 molecule of MgCl2. And so you simply multiply this number by 2. All right, so when you multiply it by 2, you can clear your answer and multiply it by 2. Or if you do it just like this, your answer is going to be double this, but it's going to be a 2.53 times 10 to the 23rd atoms of Cl. All right, if you clear your calculator, this would be a 2. So again, this is the uncertainty. So you have certain numbers plus one number having some uncertainty. If you multiply this by 2, you would have a 2.52, and by sig figs, that would be the same number. All right, so a possible extra credit problem on the test would be number 6. So number 6 is very difficult. Cr2O7 minus 2. I'm going to change it a little bit. H plus Cr2O7 minus 2 plus N2 yields NO3 minus plus Cr plus 3 plus H2O. All right, and so this one is a oxidation reduction. All right, so what's not extra credit is getting the oxidation numbers. And so H is plus 1. H plus, monatomic, plus 1. Here, your oxygen is minus 2. So that makes that minus 14 because there are 7 of them, which makes this a plus 12 because the overall charge is minus 2. That makes each Cr plus 6. Nitrogen, element in its natural state. Oxidation number is 0. Oxygen here, again, minus 2, but we have 3 of them. And so the nitrogen is a plus 5. Chromium, plus 3. That's the oxidation. It is plus 3. Hydrogen, plus 1. Oxygen, minus 2. All right, and so you have to see what is changing oxidation numbers. So hydrogen is the same, plus 1, not oxidizing, not reducing. Cr here is plus 6. Cr here is a plus 3. This is your 6 reduced down to 3 reduction. Half reaction. All right. Oxygen, minus 2. Oxygen, minus 2. Oxygen, minus 2. Everywhere you see oxygen, it's minus 2, not changing oxidation number. Nitrogen, 0. Nitrogen, plus 5. And so when you're going from here to here, you're going from 0. It is increasing oxidation state to plus 5. This is your oxidation. Half reaction. All right. And so your oxidizing agent, so if you wanted to oxidize your nitrogen, you would have to add this Cr2O7 minus 2. So this is your oxidizing agent. And this, if you wanted to reduce your chromium from 6 to 3, you would have to add nitrogen gas. So this is your reducing agent. All right, so that's not the extra credit. The extra credit is to now balance this. So this is a very difficult question, which would be extra credit. And extra credit would be how many electrons are being transferred. Again, extra credit. All right, so to go from a 0 to a +5, we have to lose 5 electrons per nitrogen. All right, and so right now we have N2, so we'd have to put a 2 in front. And so right now we have it times 2 nitrogens. So that is losing 10 electrons total. Here, from a +6 to a +3, we have to gain 3 electrons per chromium. And so there's 2 chromiums here, and so we have to put a 2 in front here. So we have A times 2 chromiums. So we have to gain 6 electrons. All right. For oxidation reduction, you have to have electrons gained is equal to electrons lost. The least common multiple between a 6 and a 10 is 30. So you got to multiply this one by 5. So the chromium has to be multiplied by 5. And so that is then 5 Cr2s, which makes this a 10 Cr plus 3s. Your nitrogens have to be multiplied by 3 to lose 30 electrons. All right, so there's a 3 in front of here. I shouldn't have put that 2 here because that's now a 6. All right, and you're not done. So that means you have 30 electrons transferred. All right, 30 electrons gained, 30 electrons lost. All right, now we have to balance let's do oxygens. All right, on the left side, we have 5 times 7. We have 35 oxygens. On the right, we have 18 oxygens. And so in order to balance the oxygens, we're going to need 17 waters. And so that is 35 oxygens on both sides. Now we have to do hydrogens. Hydrogens, now we have 34 H's. 34 H's from our 17 waters. And so over here, the only place we have H is here. So we need 34 H pluses. And that's why that's extra credit. So there's your balanced chemical oxidation reduction reaction. So getting the oxidation numbers is not extra credit. Getting the oxidizing half reaction, reducing half reaction, that's not extra credit. Oxidizing agent, reducing agent, that's not balancing it. That would be the extra credit. So that would be an optional thing to try to do. But you would still have to give the oxidation numbers, oxidizing agent, reducing agent. The other one here that you have on 6 is MnO4 minus plus Fe plus 2 goes to Mn plus 2 plus Fe plus 3. All right, so in this one, we're not going to bother balancing the reaction. What we're going to do is get our oxidation numbers. Mn, O, Fe, Mn, Fe. All right, and so again, oxygen minus 2. That is 4 of them. That is minus 8. Mn has to be plus 7. Plus 7 minus 8 is minus 1. Iron plus 2 is plus 2. Mn plus 2 is plus 2. Fe plus 3 is plus 3. So this should be a very easy give the oxidation numbers. All right, so then you'll have to see what is being oxidized. Well, the one that increases oxidation state, this is your oxidation half reaction. The one that is being reduced, a plus 7 reduced down to plus 2, this is your reduction half reaction. All right, so if we wanted to oxidize the iron plus 2 to iron plus 3, we have to add an oxidizing agent. So the MnO4 minus is the oxidizing agent. To reduce the MnO4, we'd have to add a reducing agent. All right, and so that would be what you would have to do for the test. You would have to label the oxidation numbers, the oxidation half reaction, reduction half reaction, the oxidizing agent, and the reducing agent. We will do the rest of those tomorrow.